My name is Brian Bulkowski. I am the CTO and one of the founders here at Aerospike. This is part of our continuing series of Scale Warrior meetups. And our goal in this meetup is to try to share information among the community of folks really building high-scale systems. And our goal in hosting this is simply to allow you all to mix and mingle, share stories, technology that works, technology that doesn't work, because that's what we're about, and what excites us is high-scale systems. This particular meetup is about titled "Why is Micron 5 times faster than Fusion I/O?" which was a inflammatory topic to try to see who would show up, and we certainly have a who's who, the backbenchers there, Neil and the ex-CTO of Fusion I/O, and Jonathan from Violin, so a lot of well-known people within Flash here. So Scott told me from Micron, who will follow me, that he wants to keep it interactive, so anyone here who wants to call him on any of his claims, please do so. It's our goal here at Aerospike. Let's keep it light and interactive, but try to really share some information. So the reason why we at Aerospike care about Flash is because the economics of DRAM change the world a bit with big data. You can still get a lot of the performance, in-memory performance of RAM when you switch over to Flash. So I'm going to spend just a couple minutes talking about what we see and why some of our results in testing Micron's products. We test everyone's products and we try to find the right fit across the SSD and Flash universe for different products. But some of the Micron results kind of surprised us, which is why we wanted to have Scott up here and some of the folks from Micron to try to explain what's going on. So the ecosystem that we see coming together in big data involves not just the Hadoop focus of analytics and analytics warehouses, but also a high-performance real-time data store. Because once you have analytics, what are you going to do with it? It's nice to have presentations from your bosses to make, big, large-scale determinations, whether to put a store here or there, a wind farm here or there. But what about a millisecond by millisecond basis of optimizations, fraud detection, et cetera? So there's a lot of different tech stack changes that we've seen across our customer base, as was, for example, some of the changes in app servers moving to Node and Nginx and away from Apache and Tomcat. You still see a lot of Apache and Tomcat, but some of those other services are coming along as well. So the kind of deployments that we see that involve real-time data stores on the front edge of your system do involve a lot of big analytics systems, some of which are still using rotational disk because table scan analytics, where you have to see all of your data, is still very powerful, but also being able to have quick analytics and quick data store is important. So what are some examples of what you would use Flash-based big data for? First of all, we're seeing some very fast MapReduce times. So being able to actually do MapReduce style queries within milliseconds as opposed to hours is one of the side effects of using Flash. Because instead of having to roll over all of your data, you can use an index, look at a subset, still apply your MapReduce style of architecture. Examples like, well, what if I really do want to track every IP address that I've ever seen from every single customer and look at click tracks, user data tracks over every IP address? So these are some of the examples that we see. An example of merchant risk and fraud, right? It's been surprising to me how much fraud detection there is because, well, everything has fraud. Just like if you have advertising, you have fraudulent ads and you have malware. If you have transactions with credit cards, you have people doing that. You have fraud within gaming. You have bots trying to disrupt your games. You have people trying to steal different, insert themselves into different artifacts. So these kinds of patterns are in multiple different high-scale applications. And so we see, first of all, trying to use more data in these forms of computations, as well as using new computational patterns, not just queries and queries and sort of those old rule-based systems that you see within financial systems. We're starting to see stream analysis with using things like storm integration. So there's the idea that you can use in-flight analytics. You've got all your data flowing into a Hadoop cluster or an analytics cluster. What if you don't have to store all of it? Of course, you still need a data store, because just simply looking at this one message isn't usually that interesting a computation. You want to look at a historical piece of IP address, clickstream address, etc. So you want to be able to share that. You want to have shared models. For example, when you're doing modeling such as curve fitting for predictive analytics, you can now do that on the fly over larger data sets when you have flash and in-memory. Within advertising, of course, you have a lot of interesting optimizations as well. So are people really doing this? Absolutely. You know, one of these, I like this slide because it just shows you know, $200 million a year, and they're all using proprietary software for this, right? So that was just one number. We know that there's actually a lot more flash out there. But if you're competing with the Facebooks and Apples and Googles of the world, you better also be on this train. And flash just has a dramatic change in what you can do on a particular budget. I often think, you know, there's the amount that I can talk a manager into when I'm starting a project. And I sort of fix that number in my head. Okay, let's see, I think I can talk him into 150K. How am I going to best use that 150K? Well, if I'm using, if I can get to 10 terabytes of online random data, then I can present a more effective project for the amount of money. So I want to be able to scale up my ambitions based on a particular dollar value of project. As a real world example, and this is an example that we're going to be talking about a little bit tomorrow. So a woman named Sharon Paisner, who's one of the architects at Brightroll, will be presenting tomorrow some of her tech stack and what she's doing with this. This is actually with a Micron card as well. What's interesting is that 4 of these things will actually get you about 500,000 transactions a second at a reasonable cost. So again, this is the kind of number I can often talk a manager into. These kinds of numbers are a little rough. And just in case you think that flash is a you know, big data $100,000 kind of problem, this was a whiteboard that I did with a customer in China, and they simply wanted 200 gig, and they said, well, 200 gig, why don't I just use DRAM and Redis? And flash was going to save them about $20,000 just in their first hardware buy. So that's the kind of thing that gets people excited. And then, oh, as you scale it up, it gets better and better. So at Aerospike, we're all about measuring what these flash drives can do and creating a database that optimally uses it. So we have a tool called ACT, the Aerospike Certification Tool, and it uses a particular pattern of reads and writes. You can read about it at the GitHub page. So when we first tried the Micron P320, it was very different from a lot of the older Micron SSD-based systems that we saw. When we do testing, what we do is we ramp up the load and we look at latency figures. So this is the percent under 1 millisecond, 8 milliseconds, and 64 milliseconds of reads. And this is with 1.5K reads, but under a sustained write load. And that's really what makes a difference to us when we're looking at drives for a lot of our use cases, because you've got this behavior constantly pouring in. It never stops. You don't have a 15 minutes for a drive to be able to catch up. So this particular test that we ran was running with very, very low, less than 1 millisecond times, still with very high rates on a single card at a very reasonable price point. So I sat down with one of this senior application engineers, a guy named Raj from Micron, down at their offices, and simply asked them how the heck did they do that, given that they're using a lot of the same fab lines and chips that Intel is. So I'm hoping that we're going to get some really good answers to that. As an example of some other devices we ran similar tests against, with 6K reads compared to, remember, 150K, 6K reads, here's the kind of numbers we expect out of Intel's S3700s, which are also very nice drives, right? And you can also stack up a lot of drives in a single chassis. But you're seeing numbers like 1.6 and 12% against only 6K reads instead of 150. And the Fusion IO Drive 2 was clocking in at these kind of rates, again at the $8 price point. And of course, the Intels are at a $3 gig price point. So again, there's different devices and different drives for different problems. So that's the end of what I have to say about this, because I'd like to get Scott on stage and have him explain and talk about how Micron is seeing the flash market and the products they're bringing out. And he said, again, please interrupt him and give him some challenges in case there's anything you want more detail about.
But I'd like to say thank you to those that are doing the repeat event. I know we had a lot of fun last week when we got kicked out by the fireman. I wanted to get a picture, but he was just not looking like he was in the mood for me to take his photograph. So, but yeah, we had a little bit of fun last week, so I'm glad we were able to get back so soon and be able to take advantage of going forward with this meetup. So the purpose of our little presentation here is to give you an insight onto where Micron not only sees the SSD market, what Micron SSDs are about, and just give you a little look forward in time and just have a little bit of fun as well. I mean, it's after hours. We're here to have a learning activity, but also have a little bit of fun. So to Brian's point, please feel free. The SSDs have been kind of my life since 2007 in various different forms, so I've had a little bit of fun with this. And everybody always asks me, well, is it the year of the SSD? And I have to honestly say that I think we finally, after being doing this for 6+ years, we're finally at the year of SSD as we see the adoption rates, the way the products are being developed, the platforms that we're able to use for them. So with that said, how do we continue to grow the market? What is it that's driving SSD adoption? Well, the first thing we always get is to the point Brian made is there's always this dollar per gigabyte play. There's always how much do I need to convince someone a way to use my product? So what do you need to hear? What is it that you want to hear from me? What metric is it that drives the way to be able to solve the problem you need with an SSD product? We all know they're really cool. We all know they're really fast and great. I can sell them to you at various different price points. I have a whole bunch of different versions of our drives over there, which we'll kind of highlight here in a minute. But these are some of the conversations we've had, anywhere from IOPS per dollar, IOPS per watt. A couple of the fun ones for our European friends, that they're very space constrained in a lot of instances. So it's IOPS per cubic inch of floor space I need to occupy to be able to get the performance. IOPS per U of rack space. So is it a 1U, is it a 2U, is it a 3U, a 4U footprint that I have to utilize to get there? And then, of course, durability and productivity. One of the things that we've already talked about, or I had a conversation with someone here tonight, is, well, we know they have a finite life. How do you deal with it? Well, that's a whole nother conversation. We can talk about that all we want. And in fact, it's wonderful. We actually have the show next week for any of those of you that aren't aware. Flash Memory Summit next week is down at the Santa Clara Convention Center. And you can talk to anybody about SSDs at that show because there's just a lot going on there. So are we there yet? Are we really getting what we need out of SSDs? So this is a different view. One thing that's unique about this is Micron's IT department finally listening to Micron marketing, saying you need to use your own products. So we had a platform within the Micron fold where they were doing a bunch of analytics, and the red line here represents what they were getting from a amount of time it took and a number of transactions they were able to complete using just a hard drive implementation for one of our database platforms. We said, well, just throw some SSDs in it. Do nothing but throw some SSDs in it. We gave them a couple, in this case, SATA SSDs. And you can see the platform wasn't quite sure what to do with it. It got some really good performance, but then it ran out of the ability to keep up with the SSD. The platform wasn't designed to use the SSD product. So we still managed to save time, do an improvement in initial performance, but there was a fall off. And it wasn't a fall off because my drive didn't work. It was a fall off because the platform that it was put in had no other architecture tailored to it, no other software added to it, no other value-added benefit other than just putting it in. And the interesting thing is, when we first started launching SSDs into the marketplace, this was a real problem. Everybody said, well, it worked great for a minute, but why doesn't it keep working? And that's why partners like Aerospike and these development tools, things like ACT, are able to help us better understand and better define how to take it to the next step and make something more of it with the SSD architectures. So to Brian's point, why Micron? Navigating to the right solutions. It's very interesting that the market for SSDs has grown dramatically over time. So it's always fun to take a step back and look at the historical view of things. I mean, I'm not sure how many of you have noticed, but bell bottoms are starting to come back in. The Ray-Ban Wayfarer is really popular again. So if you look at the historical view of the hard drive market, it's interesting to see the number of suppliers that jumped into the market when something was there to create a need for it. So the IBM PC came out back in 1985, and all of a sudden we went from just a couple of key, very large disk drive manufacturers to a slew of drive manufacturers. Well, as we got over time, innovation, ways to make things different, ways of change, we started to see that completely drop back off. And now we're down to basically 2 real suppliers in the market, Seagate and WD, for some form of a hard drive market. It was because of technology shifts, things that were able to be integrated and developed by the people that started it that are able to finish it. So you've got things like thin film recording, the shrinking of drives, vertical recording, we're now at heat-assisted technologies. Well, what if we overlap the SSD play on this as well? Same kind of spike, same kind of introduction of a new type of personal computing or portable computing, the notebook as we deemed it back then, but a slightly different view of it. There's more people in the world, there's more opportunity to have a number of companies that are generating these tool sets too. Again, you have to look at the concepts back of who starts it, what are you using, what's unique about these portfolios. So what we did is a friend of mine at Objective Analysis, Mr. Handy, put together a small list of potential SSD suppliers. And this is a list from back in about 2009. And I've updated it with red of all the companies that have been out of business or acquired over the last couple of years. And you can see it's continuing to shrink over time. We've kind of hit that same exact, does history repeat itself? Because we've got a whole bunch of suppliers that came into the market, but we're starting to see them go away again. What's driving the going away of the products? There's unique innovation in technology. If you look at our the NAND flash itself, the media that we're using, just like it does on the hard drive market, there's a significant advantage to having ownership of the NAND. And that's one of the key aspects of being Micron. A lot of people don't know who Micron is when you say SSDs, or you don't know who Micron is when you talk about storage, because we're known as a very good component company. As of last week, with the close of our latest acquisition of Elpida, we're the 2nd largest semiconductor manufacturer in the world, but how does that fit into the storage market? So that's one of the key things that's unique about us, is that we're starting to drive towards the storage play, not so much the component play. So I don't know how many trade shows I've been to where we put up a really pretty picture of a big wafer and sit in front of an SSD, and they're like, oh yeah, you're the component guy. Do you put parts in there? Well, we put parts, we put controllers, we put firmware, we put all of the design aspects of those drives. So we're going to continue to see this grow, especially along the lines of this enterprise storage market. Now what's unique is back in 2007 when I started really getting into SSDs. I mean, if you look at my history, just a quick sidebar, I had spent about 12 years as a double E designing the semiconductor components for Micron. And then I went and got the frontal lobotomy and I became a marketing guy. So don't ask too many deep technical questions. I don't have it back up there anymore. But there was a lot of opportunity to say, I have a SSD. Then it was, well, no, I've got a client SSD and I've got an enterprise SSD. And there was a fine line of what that meant. Client was, oh, it's an SSD, it's really expensive, it's for the gamers, let them go play with it. And then there was the enterprise guys who said, it's really expensive, but it's really fast. One of the first fiber channel drives that came to market was $65 a gigabyte for 73 gigabytes. Wasn't much storage, but it was enterprise class. We're into 2013, we've got to do things differently. So we've started looking at a different model of SSD deployment. It's about performance, it's about endurance, it's about cost, and it's about what you're using it for. We're getting more intelligent with our platforms. People aren't just doing what we just showed you earlier, which was just pull out a hard drive and put in an SSD. We're actually re-architecting the structure. We're trying to do something different in the marketplace to be able to drive really, not necessarily the acceptance of SSD, but the better utilization of the SSD. It's a really cool architecture. Let's take advantage of it. So let's do something a little different. So you've got things like personal systems products. You've got this wonderful Web 2.0 data center storage market. You've got the high performance mission critical. I've got to store data, lots and lots of data, so I'm going to put it in some form of a server platform or major storage platform. And then you've got the class of PCIe drives. We're not sure if you want to call it a storage device or an I/O accelerator, but it's broken out in what we kind of can see as 4 unique categories. And the beauty of it is, this is the Micron spin of it. This is doing a lot of talking to our customers. What do you need products for? What type of product do you need? Is it going to go in this type of server? What kind of performance are you looking for? What kind of endurance are you looking for? At the same time, it still doesn't answer the question, how do you define the path of SSD consumption? Because you could say, for example, I'll look at a drive and I'll say, I'm going to design a notebook drive. I want to take this really low-cost MLC device, put a controller behind it, and make it work really fast in the SSD market for purposes of my notebook. Well, I really like that price point. Let's go throw it in a server, see what happens. That becomes this data center storage market. Well, can you design a product that can do both? It's not as easy as it sounds. I mean, you've got a lot of controller technologies, a lot of controller manufacturers that build SSD architectures and even get allocation of NAND, whatever the case may be. But you still have a blurring of the lines. There's no one right answer. So we've put together a portfolio of products where we've gone after as much of that market as we can. And we've kind of blurred some of those lines a little bit too. So you've got the personal systems drive. And in this case, the way we're representing it here, a little bit about kind of what it's meant for, the description of the segment as we see it. So are you doing I/O acceleration? Is it really just an accelerator? It can be used as storage, but you can also just use it to get data in and out very quickly. You're going to go replicate it somewhere else anyway, whether you're using a SQL, NoSQL, whatever type of platform. There's never just one copy of your data if you're doing a database management platform. Then you've got your business mission critical stuff. What if power gets pulled? Do I have support to protect it? Am I doing stuff to make sure that that architecture is in place? There's costs involved with power protection versus non-power protected drives. Your active data, I need it to be able to read and write a lot of data every day. If it loses power, I really don't care as long as the drive comes back up. I'm going to reload the data anyway. Remember, I've got a replicated copy somewhere. So I can save on costs in the way I architect the drive, but it's got to last a long period of time, anywhere from 3 to 5 years, while I'm doing all this with really low cost flash. And then of course this bulk storage concept. There's a lot of new unique platforms we're running into where people are writing once and reading many. I don't care how many of them you buy. Go buy a whole bunch of them. I love it. Put petabytes, exabytes of data out in a storage cluster, write to it just once and read from it as much as you want. I like that kind of architecture because I have a finite life to my product. But at the same time, the idea is here, you're going to need SATA, you're going to need SAS, you're going to need PCIe, and what about different versions of those types of products? So that's why you can see here we've got a plethora of different designs, different techniques. I'm not trying to do the Micron portfolio pitch, so you can certainly review the information later as far as what each of these particular products are. But when you start talking back to the graph of history repeating itself, what can Micron do for you, or what does Micron do for you with our SSD portfolio to satisfy the needs of all these different segments? So we've come up with a kind of a menu. We call it the SSD Design menu for 24/7, 365 operations. We've created a set of tools that we can utilize across different storage architectures for enhancement, for performance, for reliability, for durability. Depends on what you need. Each one of our products can utilize a different version or subset or all of these products for your safety's sake. So for example, we call it Armor. Armor, the idea here is you're just doing a really good job of data management. Your write amplification levels are low. We're doing good management of your data as it's traveling through my controller. I've got to add stuff to it. I've got to put LBA markers to it because remember, it's random all over the drive. I don't know where I'm putting it until it's there as far as your host system is seen. We've added things like RAIN. So one of the wonderful favorite and least favorite words that are used in the storage market is RAID. RAID is wonderful because it's a duplication product, but RAID is terrible because if you do simple RAID, it's really expensive. It's 2 for 1. Well, what if you build RAID into the device level at what we're calling the RAIN, or redundant array of independent NAND? What I'm doing here is for every bit of data you write, I'm adding parity to it into the drive, so that overcoming some of the flash constraints that you're going to run into as you get into smaller and smaller geometries and architectures. Well, the question is, well, what do you use? Do you 5+1, 7+1, 128+1? It's tailored for the product, for the segment, for the socket. We can adjust it based on technology node and what the customer is using it for. And therefore, you're able to manage and manipulate the NAND level, and you can help alleviate some of the RAID level concerns or even the wear-out concerns. Because if you have a specific device go bad, that's fine. I can lose an entire 8-die stack device on my PCIe architecture and recover all your data. And you don't even see it happen. That's the beauty of the type of architectures that we're putting into these things. Recal, well, there's this wonderful thing that we have about devices wearing out over time. It takes longer and longer to program them because we've got things like, device physics level charge traps or oxide tunneling issues that are going on. How do we mitigate some of that? Well, we have this really cool thing that Micron somewhat did a disservice in the industry by introducing in 2009 called eMLC, or Enterprise Class MLC. All we did was slow it down. It made it last longer because we slowed it down because the customer said, slow it down, make it last longer. The trick is, it's a one-time shot. If you buy an eMLC-based product, that's great. It's slower, it'll last longer, but it doesn't do anything else for you. You've just got a controller and NAND. Recal has the ability to go into the device and proactively change both the read algorithms and the program algorithms internal to the flash using the wonderful backdoors that the NAND vendor is able to utilize to recover and adjust for that over time. So you take a device that's set for 3,000 program erase cycles. In my drive, it will never reach 3,000 program erase cycles and die. It'll reach 6,000, it'll reach 9,000, it'll reach 12,000 because I'm constantly adjusting those parameters that are being set or being shifted by the oxide wear out or by the device level wear out, so I can extend the life of your drive. So it's no longer a how many cycles do I get discussion. It's, well, how long do you want it to last? I can adjust for that. And then, of course, optimized NAND. We've actually got some products. To Brian's point, we have a shared fabrication facility called IMFT. Intel gets 49% of one of our fabs. We get the rest, 51% of that fab, and the 4 other fabs are now Micron wholly owned. So we're getting 80% of the joint output. All the R&D is a little bit shared, but some of the uniqueness is we can do something they can't. So we've actually got products on the market today that are utilizing a NAND architecture that was customized for SSDs. So you as a consumer can go buy my raw NAND component. Well, I have SSDs that not only use that NAND component, but I've got SSDs that use a variation of that component that you'll never see on the open market, but it's utilized in my SSDs, again, to prolong the life of the product, give you a high-quality storage device. And of course, as we develop new things, you'll see a slide here later talking about where we're going with future technologies. We can keep adding to this. It's our firmware. We own the device. We own the design. Everything about these products is 100% Micron built. So take a quick snapshot. Brian was kind enough to highlight some of the data that we had from the P320H, and I wanted to talk about also our P420M. You've got SLC devices. Someone earlier mentioned the concept of it being super large cost. I like that one. That's my new favorite. And then MLC, of course, we could come up with all kinds of acronyms for that as well. But well, much less? Is it much less cost? There you go. I love it. One thing that's unique about the PCIe architectures, we're all used to seeing this. This is the PCI half height, half length. You've got full height, full length, full height, half length, all those fun architectures. We were able to work with a partner and introduce the world's first 2.5-inch PCIe. This is one of those, wait, I thought we were thinking outside the box with flash. Why are we going back in the box? Well, how many of us buy a storage box that has at least one hard drive slot in it? That's the purpose of going back in the box. We're able to take advantage of those types of architectures. We also have industry-leading performance. You saw Brian highlight some of the metrics. We've got a lot of different review sites that have done analysis of our PCIe drives. We're just fast. And there's a lot of things about it. One of the key design differences is we have a hardware-based ASIC design. So there's a lot of hardware acceleration between the ECC, the data mapping, and all those types of architectures. And there's a lot of flash back there. I mean, even for a drive that's 175 gigabytes all the way up to 1.4 terabytes, we've got over 30 channels of flash in this thing. We can do more things with more devices in more places than any of the SATA or SAS products, because most of those are 8-channel, maybe 10-channel controllers. So that's how we're able to catch up to the curve that PCIe offers us from an interface bandwidth. Well, great. I've told you about the flash. I've told you about our cool architecture. We're vertically integrated. Let's get a little techie for just a minute. And this is a marketing techie, so forgive me. Feel free to ask questions, and I'll say I don't know. But you can see we have to map data into the device. And how do you map the data? Well, if I just write it literally in sequence to the device like you can with the hard drive, that's great until you hit the end of that device, and I got to go start over again. I got cleanup procedures. I've got garbage collection with this whole thing about write amplification. If I have to read, verify, or read, modify, write, that's a 2-to-1 write amplification right there. So we've actually taken the effort to go through and say, well, I've got a logical unit that's coming in from my host, and I've got 32 channels. Let's spread the wealth. I'm going to actually break things up and spread it across multiple devices. Benefits to you: faster write performance, better reliability, less likelihood of losing your data in one single device. And we're able to manipulate that and manage that and take care of it with those types of architectures behind writing into the actual thing. We'll rotate between the channels, we'll rotate between the LUNs that are going in, and we can actually do a lot of that read while write or write while read architectures. One of the beauties of our data sheets, and a wonderful marketing gimmick for anybody producing a product that has a speed associated to it, is I can do 100% this, or I can do 100% this. Not very many people highlight what you do anywhere in between. And we found out way back in about 2008, a lot of the SSDs that thought they were really fast, if you did 1% reads while writes, or 1% writes while reads, you had this huge bathtub. So at 50-50, you kind of expected this linear curve. I'm really slow on writes because I've got the NAND program times to worry about. I'm really fast on reads because there's just no latency there. It should be a straight line. Most of the SSDs in the early market weren't. They were this nice, lovely bathtub. This is a way to get rid of that kind of architecture. We know what the flash program times are, so we're going to manipulate the data going into the drive to ensure that we're never getting caught by the program time unless it's at one of those 100% level marks. So another aspect of PCIe that's very unique is driver. Drivers are a big topic because how do I use your drive? It's PCIe. PCIe is a great transport layer, but when it was first conceived, it was never meant to be a storage location. So we had to come up with creative ways to make that work. All of the devices today are HCI based. There's a couple of them that are coming out shortly that are utilizing some new architectures that we've been helping found, like NVMe and SCSI Express, SOP, those kinds of things, to kind of consolidate it. But until we get there, we've got to have drivers for today's time. So you can see here what we've done is we went and actually rewrote a mini port driver. It's a pure to MSAHCI. It helps with the performance. It gives us the ability to manipulate the queue depths of the systems. And it doesn't replace the standard driver set. It doesn't require you to load this huge software set. I don't have to ship a USB key with my drive. It's got a very simple low-level driver. You plug it in. The BIOS can now recognize it. You can boot from it. It looks to the system like any other drive in the box. There's some disadvantages to that. And I mean, we can make up with that with partnerships with companies like Aerospike to do some testing on it for us and help us showcase the ways that this works. Or we can partner with other aspects of software. We're also developing our own for that extra layer, that cache layer, whatever the case may be. But we have the ability to not utilize host resources. Everything's done internal to the drive. Well, Windows is great. What about the Linux platform side of things? You can see here the original file structure that they were going through was going to be utilizing a traditional driver stack to be able to get into the drive and back out. Well, things are limited when you try to reutilize an AHCI driver for a Linux platform, when it's Windows-based and you're just tagging on the other aspects of it. So what we were able to do is manipulate it and generate a much smaller footprint of how to get data in and out of our drive. It allows you to do things like increase queue depths, be more economical with your platform, and just give you back the speed that you're looking for. From implementation benefits, the real meat of the why, you get a larger queue. You get the 256 queue depth that you're looking for out of the gate. You get the layered architecture, so we can talk PCIe level block or HCI. They're all manipulated well together. They work hand in hand with each other. We also have the ability to do this concept of workarounds for the firmware and hardware by customer. So there's been some announcements in the past by some of the big guys where we're the hardware solution to their software platform. Well, it's not as simple as just giving them a drive saying, yes, go qualify it, slap your software on. We had to actually partner with those companies to be able to say, okay, what do you need changed in the driver? What do you need changed in this level of firmware to be able to manipulate and monopolize on the interaction of those two platforms to be able to ship our end customers a very value-added product. And then, of course, power management. 25 watts on a slot, we never go over that. When you talk about this 2.5-inch architecture, there's a lot less power allowed for that socket. We're all used to a 15-watt slot for a SAS or SATA drive in the front of a box. It's got all integrated into the controller of the device. We can manipulate all of that with our Asic design. So what does it relate to? Here's our performance numbers. The one and only performance slide I've got in here. Again, just showcasing 4K random read and write aspects, and then the sequential bandwidth numbers. It really is fast. We all know that. So a little bit of that kind of TCO view again. This is taking a look at, in this case, we went for more of the target of what does it take to get to a certain I/O level. The hard part with TCO for anybody is what metric do I use to justify the TCO? Is it a number of IOPS? Is it a size capacity limitation? Is it a footprint? Whatever the case may be. So we've got multiple versions of this platform. But any way you look at it, it always comes out, especially when you get into power, cooling, cost, footprint, hardware buy to get the number of drives equivalent, that you save a lot of money when it comes to the TCO model. So everybody said PCIe drives are really expensive. They are, but you get a lot of benefit from them too at the same time. So I mentioned earlier that moving back in the box, this 2.5-inch architecture. I do have a 2.5-inch PCIe drive over there. One thing I wanted to highlight is we did this as a first person to launch a product, but we did it in the way that we're not doing it where you have to buy from Micron. Yes, I love getting the business and I want to be your sole source, but I don't think anybody in the room is happy with the concept of sole source. So we worked with the industry, this working group called SSDformfactor.org, that came up with a footprint for the edge connector and the requirements of what that drive has as far as power limitations, performance expectations, number of lanes, and how it can work well with existing platforms. It's PCIe in the front of a box. We've all got great SAS backplanes, but nobody's got a PCIe backplane yet, save, in this case, one platform from Dell, which was our lead partner with this program. But that's this year. What about next year? What about 15? If we always have to keep changing the hardware footprint, it doesn't solve the problem. We got to make something consistent. So we came up with this concept of this 8639 combo connector. And you can see up here, it's a little bit harder to read from a distance, but The blue represents the traditional SATA SAS implementations, and the red represents the PCIe. We use the spare plastic. So you can put any one type of drive into any given socket when it's designed right for platforms to be able to utilize this drive. So if I want SAS drives, great. I can give you SAS SSDs, I can give you SAS, you can go buy a SAS hard drive. If you want PCIe in the slot, as long as it's been designed for it, which we're working with pretty much every metal bender out there to do so, you can use a PCIe drive in its place. And it allows for the flexibility of hot pluggability or orderly removal, as the official designation is from the working group. So as I mentioned today, the part numbers for the connectors are standard. Foxconn's the first one to market with it. Again, they're one of the founding members of the working group. And Dell was driving it. So the Dell R720 and 820 are the first true designs that are shipping today where you can get this PCIe backplane. There are more coming, I'll tell you right now. And there's several local Valley guys that are iron benders that are coming out with some end of this year, early next year. We've got a couple of overseas guys as well that are building platforms. These first platforms were designed to be able to utilize 4 PCIe SSDs and their own unified backplane. So if you bought the box design for it, you could only use the 4 PCIe slots, or you could use the other slots for SAS and SATA, but you couldn't do cross-pollination because it was a first launch product. They wanted to get it to market. All of the new platforms coming out in 14 and into 15, they're going to allow for all 3 drives to work in a single backplane. Now, that's great. I got massive bandwidth now. PCIe Gen 3, 24 drives. Oh wait, 15 watts per drive. Oh, so we actually have to get back into the power, cooling, and can I actually get it out of the box performance discussion? So that's one reason why we're working very closely with the storage box vendors. Well, if you're going to build 24 slots, that's great, but can your box actually use it? Are you properly pitching it so that customers realize the limitations that they may have to deal with those particular platforms? And so I kind of leave it up here. What do you want from it? What is it that you see, say, PCIe, SATA, SAS, from your SSD to make it the most viable solution for you? We've got lots of ways to spin data. We've got lots of real-time data, lots of theoretical data that we can showcase. All of the SSD vendors do, but our goal is to make sure that we work with you, no matter how big, no matter how small, to solve that solution set. So why not take a look? Well, what's coming next? Well, I've got you. I actually still got some attention. I love it. Moving into the new storage era, we're all familiar. Local storage is slowing down in favor of this cloud concept. We've all got the tablets with iCloud, or we've all got the Google tablets with the platforms for purposes of Dropbox and all those things. You've got Microsoft with SkyDrive. Great. Go out and keep buying it because all those back ends need my speed to make them work. It's a wonderful thing. We're utilized in a lot of these new database platforms or server platforms to be able to generate the local storage replacement for those devices that are being driven by the portable concepts. And we also have to make sure we're keeping it moving forward. So PCIe is new. It's the latest and greatest. We've finally got it architected right. What's the next step? How about smaller PCIe? You'll notice that there was an announcement recently about the new portable computing platform from Apple that has a gum stick PCIe drive. Been there, done that. We've had a SATA equivalent of that product since before they conceptualized it. We're working on the PCIe solutions now. So then now what? What do I do with that? If I've got 512 gigabytes in a piece of gum, well, how can I use that in a server? I know it works great in a notebook platform, but what if I get beyond that? As we move on even deeper into the drive, back again to this, I'm a component guy a little bit, so I got to spin my component pitch. There's a lot of things going on the back side of these drives. We've all dealt with the hard drives going through the changes of magnetic recording to heat assisted to vertical. We've got shingle recording. The same thing's happening on NAND media, and we're doing our best to make sure that for the storage folks that we do our best job to not have that become a problem either. And so we've thought about it, doing a lot of things. Of course, big data analytics is one of the key players in that because we've got to figure out a way to make our shrinking NAND with shrinking specs last just as long or longer than they do today with the same performances that you're getting. So there's a lot of different ways you can do it. You can look at DRAM solutions. We've got some very unique things like our hybrid memory cube, or this what we're calling a 2.5D system, which utilizes DRAM, NAND, and a few other things in a DRAM replacement footprint. You've got the SSDs, of course, that we're working on. Yes, we do make them. We're not just enabling them as well. And then, of course, there's NAND innovations. We've got things like 3D NAND architectures that are already baked, that are working in our R&D fabs. We're working on rolling them out into production. And there's multiple ways to pull that off, too. Why is all of that important? Well, it's that wonderful thing known as Moore's Law. He's our friend, he's our enemy. We're finally coming to the point where we're not able to keep up or take advantage of the constant doubling of architectures. If you look back in time when I first started designing NAND devices, we were at 90 nanometers. And I could take up as much real estate as I wanted because it didn't really matter because the array was so much bigger and so much denser, the periphery was no big deal. Well, then we went to 70, then we went to 50, then we went to 40, 30, 25, 20, 16, 12. We can't double it anymore. It's just not physically capable of doing that. Even when we go 3D, we're going vertical. Great, you got your real estate back. You can go larger capacities. You've introduced a whole nother dynamics of device physics you never had to deal with before. There's no tub anymore. I don't have this nice little piece of bare silicon at the bottom of all my gates to recover from that. So we're starting to see this reduction in the ability to be able to drive bit cost reductions. We've got to find other ways to do it. And that's part of what we're after as far as making sure that for the next couple of nodes that we can continue to stay on top of it. What's next? What's beyond NAND? Well, we've got live PCM devices today. They're shipping in wireless cell phones because they're small capacity. There's scalability there. They're at 40 nanometers today. We've got plenty of leg room to get them down to 12 while getting the capacity up. We've actually got working prototypes of PCIe-based interface with PCM memory, unlimited endurance, zero latency effectively, all on a storage device that fits in a PCIe slot. Trouble? Capacity. Well, there's the TCO model for that. 64 gigabytes enough? At that speed, it is plenty fast for some people. So I've drained your brain a little bit. I've given you the big Micron pitch. So this is the part of the evening where I kind of call it quits and say, well, let's just have a little bit of fun with data. We all know big data. We all know what's going on. I have a wonderful friend of mine at Micron who's an applications engineer on our SSD projects. And we said, we want to come up with the endurance numbers. So this is that write-where limitation problem. I've got a PCIe drive at 700 gigabytes. How long or how much data can I write to it? We determined that on that particular drive, the TBW for it was 50 petabytes. So normally, you might go home, lay down, and start counting sheep if you can't fall asleep. Not Doug. Doug is just way too fun for that. So he started thinking, well, what does that really mean to me? So he started doing some math. So 50 petabytes, and you'll watch as this graphic goes from a gigabyte to petabytes of information on the side. He found out that, well, I could back up my entire laptop hard drive 210,000 times, and at current rates of speed, it would take 20 years to get that data stored. So am I going to wear the drive out in my lifetime? I'm not really worried about it. Well, how about DVDs? He could archive 11 million standard DVDs, so cut that in half for Blu-ray, and it'd take 1,300 years to watch all of those videos. So petabytes of wear, terabytes of wear, yeah, there's a limitation, but it's not really a gate for us. We have ways around it. And especially as we get into this big idea of really low-cost MLC solutions, people are just throwing the drives away. Yeah, if it lasts a year and a half, great. That's all I need at the price point it's at today. Finally, a petabyte is a lot of data. 35 MP3 files in every iPod ever sold since Apple started, hard drive based or not. So you can see over here again, what we can do with 50 petabytes of wear characteristics. Now that's the extreme case. Our SLC PCIe drive is rock solid. You'll never wear the thing out. We do have client level drives that you could wear out if you put them in a server and ran 100% write workloads on them. But the goal is we've got everything in between too. So when it comes to looking for an SSD solution, it's not a one-stop shop. You need more than one choice, and you need the expertise of the media to really make it work, especially as we move into the next couple of very trying years of things like vertical NAND and these really unique ways that media is changing. So with that said, I'm going to open it up to questions. I apparently didn't get any heckling in the middle, even though Brian offered the opportunity. So anybody questions, I'll do my best to answer anything you have, as technical or as fun or as competitive as you want to be.
Touched a little on NVMe after the gates here, right? What's the time frame?
So the question for the purpose of the video is, I mentioned NVMe and what's the time frame. The time frame for NVMe itself as an architecture is now. The solution sets are starting to come out. The first real chipset platform that's going to support that is going to be the Grantley platform. Micron does have an NVMe solution in progress. I'm not allowed to give a release date because then I'll get shot if it doesn't hit it, but it's in the very near future. And it was alluded to also by our strategic director. So, but yeah, there are some solutions that are starting to come out in sample phase now from other sources.
So why do you think you're behind Samsung in that?
So the question is, why am I behind Samsung on NVMe? back to the very beginning of the conversation where Micron's a component company working on becoming a more SSD-centric company, they did have a leg up on us. They were pushing SSDs into the market in 2005. We started in 2007. We're growing quickly. It's a matter of bandwidth, resources, and what's really needed. If I have NVMe right now today, can I sell it to anybody? There's not a platform to utilize it yet. So we're keeping as much as we can on pace with platform launches and available resources to utilize them.
I'll buy.
You'll buy? All right. Found my first customer. Yes?
How many CPUs do you have in your PCIe controller?
It's a multi-core. So the question was, how many CPUs are in the PCIe controller? It is multi-core. It is no secret that we did partner with IDT. So we did utilize a lot of the IDT base architecture on their highest core count. And to be honest, I don't remember the core count of that solution set. Basically, the way the marriage worked is we're a memory company. We do a great job of putting memory out of our fabs, but it's not meant for processors. So IDT fabs our controller device, and they gave us the PCIe front end. Everything from where it leaves the host side of that interface to the NAND management into the raw NAND is Micron IP. So they do have several processors in there to be able to, we've got at least one processor per couple of channels in there to be able to manage the data flow through the controller.
You see your controller enabling you to support your 3D stack. What do you need to change that?
So the question is our current controller able to support 3D stacks and other uniquenesses of the new medias coming out? The current controller, no. We have internal code names for our products, and this one's Gen 1. Our Gen 2 product is going to be shipping here very shortly, our NVMe compliant product. It's designed to support current technology plus forward-looking technologies. It is an ASIC, so if I do change something fundamental with architecture, I have to be able to adjust for that with the Asic design. I don't have the flexibility in some aspects of using that from a gate point of view. So we are planning ahead. Again, we design the NAND, so we know what's coming. So before we turn our next generation NAND device on in a fab, our SSD team's already been working with it from a controller point of view.
Correct me if I'm wrong. I saw two numbers. Previous speaker show a number. The write speed is about 200 megabytes per second. In your slide, you show some number is more than 2 gigabytes per second. So why there's like a 10 times difference?
That is the key question every customer ever asks us. So the question, again, for purposes of posterity's sake, is Brian was kind enough to show some numbers with his tool and his workload. We showed our numbers and our workload. So the question is, why is there such a discrepancy? Again, our data, for purposes of that particular graphic, it's great to be able to show competitive landscape, and so you're going to do best what fits best. Ours was a 4K random read and random write workload for the random numbers, and for the sequential gigabytes per second numbers, 128K packet size. Brian's numbers were based on the ACT tool, which utilizes his read-write mix, which is different, and then, of course, the transfer sizes were different. So it just comes down to which way that you're putting the number to the page. But if you do 100% sequential writes to our drive, which is somewhat unrealistic, you'll get gigabytes of bandwidth. If you put a couple percent read in there, it's not the bathtub, and we've got data to show that.
Have you done any tests? For example, I have a 10 gigabit line rate comes in, like 10 gigabit NIC card. Can you save every package on the fly to your device?
So the question is, he's got a 10 gig E line coming in. Can we save every single packet coming in? From that point of view, we're working closely with our customers that design the boxes. We're the drive guys, so whatever you can fish over the PCIe bus until you get the limit of the PCIe speeds, I can handle as far as the speed throughput. The packet sizes and the way, whatever it's touching before it hits my drive gates what my drive's able to do with it. So there are some aspects of that I can't say yes or no. I'd have to know what the platform looks like.
Have you done special optimization for PCIe 3.0?
We do. Our next generation controller is specifically designed to bandwidth limit 3.0 speeds. So if you're able to get it in and out of the box, which is what they're working on now.
So, I'm sorry, so confirm, the 420H is 2.0?
That is correct. Our current 320 and 420 series are a 2.0 product, yes. Our 3.0 products are part of our Generation 2 controller, which will be out very soon.
So I've heard that some end consumers are getting prices at nearly 50 cents a gigabyte compared to $3 to $8. When do you think Micron will be playing in that space?
So the question came back as he's heard that there's as low as 50 cents a gigabyte for devices and as high as $8 a gigabyte for devices. Is the 50 cents a gigabyte on a PCIe drive, or is it on a SATA consumer drive?
Maybe I don't care. I just want that kind of speed and sure.
Very good. So the response to my question was he doesn't care for enterprise use. So in January, Micron launched the first terabyte class drive at 62 cents a gigabyte. So it was a terabyte of storage. It's under 60 cents a gigabyte in volume, which is close to that 50-cent number. You know, marketing rounding. And that particular product was SATA-based. It was designed as a personal storage device with an uplift into the read-centric server market. So enterprise light, if you will, type of product. All the way up through that entire platform. If I went back to the portfolio map, you can see it basically 50 cents a gig up to the 8 cents a gig based on what you need the drive to do. So yes, the answer is you can have it now if you're willing to take a SATA drive at a terabyte and that you can use it in the constraints that are put upon it based on the fact that it's MLC based and centric around more of a consumer use model. And we do, to better answer that question, have several enterprise class users that are utilizing that drive today. So I don't have my nice little roadmap chart or customer chart up, but a very large red colored logoed company that does online video streaming has a platform that they've published on their blog site that showcases our 1 terabyte drive being utilized for video streaming accesses. Yes?
The controller, you are using IDT controller. How many ECC engine you have in that controller?
The current controller, because it's utilizing, in this case, 32 nanometer SLC NAND and 20 nanometer MLC NAND, is only 1 ECC per every 4 channels, because we don't need it any faster than that. There are certainly advances coming in the next generation controller for purposes of 20 and sub 20 nanometer flash devices. Yes?
IDT still up to PNCC or right? Some of the technology or some of the business?
Correct. So the question, previous question was how many ECC controllers we have, if you want to catch back up. Your question was IDT was recently sold to PMC. How does that work? So again, the partnership that Micron has with IDT is they're our fab house now for our controller. The IP in that controller is all ours and will stay ours for that particular device. They are in the process of launching their own version of a PCIe SSD controller, and several people are utilizing it in the market today. What we decided to do based on knowing where IDT was with their current solution sets and where we would like to go with it, all of our future ASIC controllers will be 100% Micron IP and fabbed at the appropriate fab house for that technology node. So we're no longer using IDT as a partner for future generation devices. Any other questions at this point? I got half the room to talk. Okay, that's all I have. So hopefully that was useful information. Again, the goal was to be a little high level, and we'll go as techy as you'd like to. And being one of our first opportunities, we thank Aerospike a lot for bringing us in here to do this. We look forward to potentially cooperating with it more and learning a lot more from you guys what you're looking for in your solutions.